Hello everyone, thanks for coming for this presentation. My name is David Velarde. I am part of the Microtechnology division at CDESI, and I'm going to talk about a microfabricated resistive temperature detector, RTD, for low-scale production. And just to mention, that low-scale production that I'm going to describe is about of 10,000 units. So first I'm going to mention the content. We are going to start with the necessity, then the design considerations, then the microfabrication methodology, and finally the conclusion. So which was the necessity? Though the pandemic of COVID-19, the World Health Organization states that high body temperature is a common symptom of COVID-19. So due to the pandemic and the shortage of medical equipment, the Mexican government states the necessity of development of this key equipment. So we were part of this call. Um, we were looking for a continuous monitoring of temperature that could be applied and used in workers and patients, not only of the health sector. And the reason is to have important points for premature diagnosis. So these are the key points that we have to consider for the design. First, I'm going to start with the medical and government considerations. These are quite extensive and complicated topics. So I'm going to try to summarize just important points related with the fabrication of the sensor, not of the entire device. And these points are characteristics that our sensor have that to be endorsed by COFEPRIS and be a certificated medical device. So the first one is related with the biocompatibility of the sensing content area. The second one is related with the immersion and uncertainty that has to be 0.1 degrees Celsius. And also our sensor have to have a measuring range capable of covering body temperatures. Also sensor have to be electrically and electromagnetically safe. And the last one is related with the place where the sensor is going to be fabricated. We have to have this certificate, the certificate of good production practices, stated by COFEPRIS. Yeah, these are points that we have to consider for the design. The second part is related with our capabilities, so I'm gonna talk about us. We are a clean room specialized in thin film devices and integrated circuits. We are capable of have minimum resolutions of about 2 microns in our designs. And it's an important point to mention that we have been previously working in temperature sensing of water, so we have background in this topic. Actually, this is the sensor that we use for monitoring water quality, and who you can see is smaller than a 1 peso coin. So we had to translate that knowledge into the new design of the new thin film sensor. And the last considerations are the physical. So I'm going to explain why we use an RTD and what is an RTD. The reason why we use an RTD is because compared with thermocouples and thermistors, it is most stable, most accurate, it has higher linearity, it will work in wide temperature ranges, and it only needs one photolithography step, so it is easy and cheaper to fabricate. And the basic function of an RTD is determined by a proportional increment of resistance when temperature is applied. This is a normal behavior of metals and could be explained in this graph. As we can see, in some point of temperature, we had a value in resistance, but when we start to increase the temperature, also there is an increment in resistance. And this could be explained with these figures. The gray circles represent atoms, and this array represent an atomic lattice, and the orange arrows represent electronic flow. So when we are close to 0 Kelvin, we see that the electronic flow is almost perfect. But when we start to increase the temperature, the atomic lattice start to vibrate. So it's more difficult to electrons to flow because they could collide with another electrons or another atoms. So the resistance increase. And this effect could be explained by the Gallen-Bardusen equation, that is a second order equation that involves the resistance at 0 degrees Celsius, two temperature coefficients that are related with the nature of the material and obviously the temperature. And this is the representation of a common RTD. They are made by a platinum wire wound in a ceramic. And the main difference between our sensor is that it's a thin film RTD, that instead of platinum, it uses nickel that is treatable and cheaper for these purposes. And it also uses a wire, but it's a thin film wire that is rated out by design. Also, it's important to mention that there is some kinds of RTDs. The most popular are the PD1000, that is related with their resistance value of 1 kilo ohm at 0 degrees Celsius. So we were looking also for this value of resistance. And to calculate that value, we use this equation of resistance in a wire that involves the resistivity of the material, the length of the wire, and is divided by its cross-sectional area that is related with the channel weight and the channel height. So taking in consideration the desired resistance value, we designed this RTD with this dimension, a pitch of 40 microns, a film thickness of 100 nanometers, and a film wire length of 6.25 centimeters. And finally, this is the design of the photomask. The circle represents a 4-inch wafer where there are 132 sensors. Each sensor is identified by a letter and a consecutive number. The letter is related with the position of the sensor in the wafer. For example, the letter A means that it's located at the center of the wafer. The letter B is the next level, and so on and so on. And this is a picture of the real bright field photomask that was with us in all the 10,000 units RTD process. And finally, it's time to talk about the microfabrication methodology. In the left side, we could see the transversal view of the process. And in the step number 1, we start with a silicon substrate. Then we have to grow silicon oxide by thermal oxidation means. We grow 300 nanometers. And this is for two important reasons. One is to isolate the initial substrate from the sensor, and the second is to have a biocompatible contact area. And the next step is the thin film deposition. So we start with the previous substrate with silicon oxide growth, and then in a single process, we deposited 20 nanometers of chrome that function as the adhesive layer of the 100 nanometers of nickel that is going to be the material of the sensor. And there are some important things to mention here. The first one is that the EVM system that we use is adapted for only one wafer per deposit, but to increase the production, we place 3 wafers for each deposit, as we can see in the video. These have two consequences. One is that we have more sensors by a production day, but we pay that increase in production with small differences in the metal thickness along the wafers. So there were some resistant differences between each RTD. So then we start with the photolithography process, starting with the chrome nickel thin film. Then we proceed with the positive photoresist deposition and the UV exposure of the bright field photomask, and then the pattern definition with the developer. Then we proceed with the metal definition, starting with the previous photolithography micropatterns. Then we proceed with the first exposed metal, that is nickel, and then we exposed also the second metal, that is chrome, both with its specific etchant. Then finally we have our sensor, so we just proceed to the photoresist removal and cleaning of the wafer. And finally, the last step is thermal treatment. The reason of this is to increase the crystallinity of nickel and homogenize all the RTDs in the wafer. Also to prepare the material for the next soldering processes to which all the RTDs will be subjected. And the thermal treatment consists of 20 minutes at 300 Celsius degrees in a nitrogen-rich environment. This slide explains why it's important the thermal treatment. And in the first graph, we show each of the RTDs with its consecutive number and also the resistance value of each RTD. Also, it's important to mention that for each wafer, we have approximately 100 functional RTDs. And with red dots, we represent the resistance of each of the RTDs along the wafer. And we can see that there's a very wide difference between each of the RTDs before the thermal treatment. But after the thermal treatment, we start to see a very narrow difference, very homogeneous values in each of the RTDs. And the reason of that is because the crystallits of nickel have bigger size, resulting in fewer grain boundaries. And this could be explained with the letter B. When done with black, we can see the diffraction pattern of nickel as deposited, and we can see that the intensities of the reflections of the material are very short. But when we start to increase the temperature to red, green, and blue color, we see an increment in the intensity of the reflections, which denotes a better crystalline quality, and that is the reason why the resistance is fewer. Also, it's important to mention that when we start to increase the temperature above 400 degrees Celsius, we start to see the presence of nickel oxides that affects the function of the sensor. And here we can see a graph that compares the theoretical values expressed by the Calimbar-Dusen equation and the experimental values that we had. And as you can see, they really match. They are really correlated. Also, we show the experimental thermal coefficients that we had, and also they really match with the coefficients of nickel. And in the second graph, we see the distribution of the values of resistance of each of the RTDs before the Tillman treatment and after the Tillman treatment. And as you can see, after the Tillman treatment, all the values are really close to each other. So at the end, each wafer has to be divided in units, so we use a laser dicing. Here is a micrography of a real final RTD. Finally, as a conclusions, we have some important points to highlight. One is that the thermal treatment homogenize and reduce the RTD resistance. The other is that the RTD resistivity shows a dependency on the crystal size and grain size. Also, the thermal treatment at 300 degrees Celsius avoids a change in resistance and sensibility by welding. The other is that the thermal treatment induces a resistant homogenizations for wafer full of RTDs. And finally, constant and specific conditions during microfabrication play an important role in repeatability and correct microfabrication. So thank you very much for your time. My name is David Velarde. I want to send a very special greeting to all the people involved with the project. There is my personal information. If you have any doubt or comment, please let me know. And it's important to mention that this project was supported by CONACYT and the projects described below. So thanks